Welcome back. Today is January 26th, and we're going to continue here trying to finish the second half of chapter 13. And this was the last slide that we mentioned the last time when we met. So for UV spectroscopy, we just have a few slides. 1, 2, 3, like 6 or 7. Now, what does UV-Vis help you with? It only does one thing. It determines the amount of conjugation. All right. So notice that in the spectrum of light, UV will be on the left side of the visible region. And this is higher energy. So think about this, the energy of the sun at this point. If we start staring at the sun, it will fry our eyes for sure. So we cannot stand the power of the UV-Vis. Of the UVs. The visible is fine. So they call it UV-Vis because they merge these two regions that goes from 200 nanometers to 800 nanometers in wavelength. And you can see here, energy-wise, you go from 150 kilojoules of moles on the right side all the way to 600 kilojoules per mole. So basically, for infrared and UV-Vis, you're looking at the energy on the left side of the spectrum will be higher energy. Higher energy, higher frequency. That means smaller wavelength, right? Because that's the opposite, according to the energy equation. All right. So UV-Vis is the reason why I didn't become a biochemist. I was looking for a professor to do research when I was an undergrad, and he had me doing a bunch of little qubits, different kinds of concentrations for compounds, and that's what I did. I was running a UV-Vis apparatus the entire day. And it turned me off right away. I was like, there's no fun in this. So then I switched to synthesis, and I loved it. So that's why I'm not really too excited about teaching about UV-Vis, but I have to. All right. So here we go. Now you know what the HOMO means. It's your highest occupied molecular orbital. And then you have your LUMO, your lowest unoccupied molecular orbital. And the highest occupied molecular orbital is usually bonding or non-bonding. And the lowest unoccupied molecular orbital is usually anti-bonding. So basically, here you have the ground state. In the ground state, if you have one electron jumping or getting excited and going to the LUMO, that becomes what is called the excited state. Now your LUMO becomes a HOMO, and the LUMO here is not shown. All right, so the typical excitation occurs from HOMO to LUMO. All right. All right. So here's a typical UV spectrum. Here you have a molecule that is conjugated. You have single, double pattern here, and that tells you that this molecule on the right side here is conjugated. Notice that you have a peak on this, a maximum peak here, or a maximum portion of the peak, and that is known as your lambda max. The lambda max for this particular peak it's shown here to be approximately 242 nanometers. All right, its absorbance is matched here on the scale to be approximately 0.45. All right, So notice that here I have, whenever you have shorter lambda, shorter wavelength, is higher energy because your frequency is higher. So shorter wavelength means higher frequency, and higher frequency is equal to higher energy. So always match the frequency with the energy. So if you have a longer wavelength, if that number is big, then you will have a smaller frequency, which will give you lower energy. All right. So learn it one way. Whenever you have duality like this, I just learn it one way. All right. Shorter lambda is equal to higher frequency equals to higher energy. All right. So handbooks now use the lambda max, and they have been able to match the lambda max with something called the molar extinction coefficient. So also known as epsilon. So you must use information from the lambda mass from that equation to find your molar extinction coefficient, which is given in reciprocal molars times reciprocal centimeters. So then the Lambert-Beer law was established, where it says that absorbance equals to the molar extinction coefficient times the concentration in molars, and multiplied by the length of the cuvette. So in this way, is the path length. It's usually 1 centimeter. All right. So lambda maxes and molar extinction coefficient maxes values are listed in tables and can be used like your melting point, your boiling point, flash point, you name it. It's a physical constant. And so, for example, for this same compound here that I show you the spectrum that is conjugated, you have a lambda max that is 242 nanometers and an molar extinction coefficient of 13,100 in methanol. So what can we do with this equation? Well, you know, if you're experimentally finding A, if you have the molar extinction coefficient and the concentration and the L, the length, you can solve for A. Likewise, you can solve for concentration, or you can even solve for Emax. The extinction coefficient that you will use here will be your extinction coefficient maximum. All right. All of that leads to this. All right. So in OCHEM, we have 3 types of electronic transitions. We're going to be using sigma, pi, and non-bonding orbitals. Usually, remember this, the energy levels start at sigma because that's your first and initial bonding. Then you have the pi, then the non-bondings, which will be right in the middle of the energetic table or diagram. And then you go up to the pi anti-bonding and the sigma anti-bonding. So the type of transition, electronic transition you can see in chemistry are sigma to sigma star, pi to pi star, and non-bonding to pi star. All right. So in other words, you can jump from here to here. That's sigma to sigma star. You can do pi to pi star, or you can do non-bonding to pi star. Those are the 3 types of electronic transitions that you will find. All right. Okay. So alkanes only have sigma orbitals because they only have sigma bonds. Therefore, the lowest energy transition that they will form will be sigma to sigma star. These transitions are very high in energy, resulting in very short wavelength, less than 200 nanometers. That means that in the UV spectrum, you will not see them. You will not see these transitions. So this effectively means we can ignore the sigma to sigma star orbitals when looking at UVVs, and that makes alkane perfect to use as solvent. They are invisible. So pi and non-bondings are the only orbitals that work for UVVs. Check this out. This slide here puts it together so you can understand this concept. Notice the energy gap between ethane. Ethane has a huge energy gap between the HOMO and the LUMO. If I was going to take one of these electrons and excite this molecule and put it over there to make the excited state of ethene, it'll take a lot of energy. Notice that higher energy means higher frequency, right? Meaning lower wavelength. Notice that the wavelength here is 165. Check that out. All right, let's go to 1,3-butadiene. Notice that the energy gap has shrunken a little bit, so it's closer. The gap is closer because it's conjugated. So if I'm going to excite this electron and make it jump right here from the HOMO to the LUMO, my energy gap is smaller, so I can overcome that easier. And so that means lower energy, lower frequency, but higher wave number, right? Higher wavelength. All right. So now we went from 165 to 217. Now we're gonna do the 1,3,5-hexatriene, and notice that now this has more conjugation. The gap has closed even more, and jumping from here to here will be easier. Therefore, you require less energy. Less energy is equal to low frequency, and lower frequency means higher wavelength. So here you have that the wavelength has increased to 253. All right, and so that's how we're going to operate. So the smaller the gap, the lower the energy. That means the longer the lambda. In this case, the lambda max. All right. Anybody understand this? Any questions up to this point? All right. I'm going to flip the page. If you think of something, let me know. I can go back and explain, but just remember this. All right? Just remember that. Let's go to the next slide. And here are some... This is a problem where we can see how this is working. And whenever you see color, it's because the molecule, it has conjugation, and the part of the molecule that absorbs the light to create this color is called a chromophore. Chromos means, color, and I don't remember what's for, but it's chromo means, from the Latin, means color. I guess for is emission or one of those terms, but I'm not sure. But anyways, the part of the molecule that absorbs the light is called a chromophore. And here you have that the pi to pi star absorption have large molar extinction coefficients. You notice that here too. Notice that as the wavelength was increasing, the extinction coefficient was also increasing. You see that? And that makes sense. So over here, whenever you have a pi to pi star, your absorptions have a larger molar extinction coefficient because basically what you're doing is, like it's shown here in green, you're jumping one electron from example from pi to pi 2 star here, and this jump is longer than the one in blue here for the non-bonding to pi star. So this jump right here is smaller. So therefore the extinction coefficient will be smaller, will be a smaller number. All right, it overcomes less energy. All right, and so your non-bonding absorptions, they're represented with an N for non-bonding, and they usually are represented as N to pi star. This absorption have a small molar extinction coefficient, usually less than 200. All right. Okay. So where do you find the non-bonding electrons? Well, you find them here. For example, your carbonyl, you have your lone pairs that are here. Those are your non-bondings because they're not making any bonds. They're just lone pairs. Those are your non-bondings. And so here, for example, acetone will have two transitions. You can have, notice that you have non-bondings here, and also you have pi bonds. Therefore, you have both. So so if I take all the, I'm not counting the sigma bonds. If I take the pi and non-bonding electrons on acetone, I will have a total of 6. So I have 2 sets of non-bonding and 1 set of pi electrons, and that's a total of 6. And so if I organize this, like I show here, pi 1 non-bonding in the middle and pi star on the top, where non-bonding will be my HOMO and the pi star is the LUMO. Notice that now I will accommodate all of these electrons, 2 in each of these orbitals. All right. So my pi to pi star absorptions in this case will be less than 200 nanometers. My non-bonding to pi star will have a lambda max with a higher wave number. I'm sorry, wavelength. I'm sorry about that. Wave number is for IR. Wavelength is for UV. And therefore the extinction coefficient maximum will be 15. Notice that this is much more less than 100. All right. So the energy that it took to make these electrons right here, one of these 2 electrons jump, will be smaller. All right. Check out benzene, for example. Benzene will have a total of 6 molecular orbitals. We have 2, 4, 6. We have 3 pairs of pair electrons. Remember that? 3 pairs of pi electrons. That's a total of 6 pi electrons. So we're going to set them up like this. In this case, I just put them like lined up like that, but in reality, you have to give it the shape of the, just like it is here, of the molecule of benzene. But anyways, here you can see that your HOMO is at pi 3, and your LUMO is at pi 4 star. So you can actually make, you actually have 2 interactions here, 2 absorptions. The pi 3 electrons can jump to pi 4 star, or you can jump to pi 5 star. And then you have 2 numbers for 2 different interactions of pi to pi star absorptions. The first one has a lambda max of 204 nanometers and a molar extinction coefficient of 7900. And the second one is also a pi to pi star with a maximum lambda of 256 and a molar extinction coefficient of 200. So the most important interaction here will be this one, because that doubles up. And for acetone, the one that will stand up the most will be this. But in this case, you have to say that you have both. You have two of those two interactions. All right, let me see. I have a question here. Okay, so those figures were the figures like the 2 in benzene. Which one are you talking about?
Like the lambda max, the extinction max.
Oh, those are given.
Okay.
Yes, thank you. All right, thank you very much. So on a test, I'll ask you, if I show you a molecule that has non-bonding electrons, you can immediately say that that molecule will have non-bonding to pi star absorptions. And if you have something like a triple bond, I mean like a benzene with the three double bonds, or triene that also has 3 sets of double bonds, those will only have pi to pi star interactions. All right, let's go to the next thing about UV vis here. All right, let me pull this down a little bit. I cannot read that well. All right, I can still not read it well. Oh, give me 1 sec. All right, let's talk about colors now. So so the visible region, this is what we see. So for a compound to have a color, it must absorb light in the visible region. When you look at the ocean and it looks so blue, that means all of the other colors have been absorbed, and the only color that that it's showing is blue. But in reality, the color that's seen is complementary to the color that is being observed. All right, check this out. For blue, for something to show blue, that means the color that has been absorbed is the orange. All right, so orange is the counter color of blue when it comes to the visible region. I think the book explains this really well. I was reading it last night. So, for example, let me show you here. Let me see if I can find it real quick. Give me a second, and I'll tell you which page is it. Chapter 13. I honestly love this book. This book is, like, in my opinion, the best OCHEM book there is. Let's see. Oh yeah, page 607. See if I can show you guys this on here. Let me stop the sharing for a second. But check this out. This page right here, this tells you the different colors that are absorbed, and also tells you, see, for example, when green is absorbed, the color that you read is red. That's the color that your eye registers. Now, if for example, green and yellow are absorbed, what you see is that purple color right there. So it's like the counter color. So that's what we see. So for example, for you to see the ocean blue, so the color that has been observed is actually being orange in the spectrum. All right. Yeah, this is really nice explained here. It's beautiful. Yeah. So let me go back to the sharing. So now you know when you see a molecule, like for example that looks yellow, you have absorbed blue violet or blue violet is the color that produces the yellow. For our eyes, what we register is yellow, but blue violet has been absorbed. Let me see something here. Oh, let me pull this down. Okay, now, I haven't finished here. For indigo blue is a famous compound. They used to use this molecule to dye jeans back in the days. They still do it. They still use it. But the cotton industry went out of business pretty much after, all the synthetic fibers came into the market, and so it kind of like ruined the people that used to produce indigo blue. The one that I have here is beta carotene. Beta carotene looks orange. So notice that the blue was absorbed, and the wavelength that is showing here is 552 nanometers. So that means that, the blue was absorbed, and what we perceive with our eyes is the color orange. All right. Likewise here for indigo blue, it's showing blue. So the lambda max is about 600 nanometers. So in this table I have here 590. So that's close enough to show blue. And for 1,2-benzanthrazine, the lambda max was 386. So it shows yellow. It could also well be in the realm of yellow-green because it's before 400 nanometers. All right, so this is what UV does. It's not as exciting as what we're going to see next. One last thing. What can you do with UV spectroscopy when determining structure? So you look in the 200 to, notice here, 200 to 800 region, but most of it is the visible region. Where's that here? So the visible region goes from 800 to 400, and the UV goes from 400 to 200. So the two combines go from 800 to 200 nanometers. And so there's some question here. It says, if there are no absorption peaks, then we can safely assume that the structure has none of the following. So there's no benzene ring, no carbonyl ring, carbonyl group, and no conjugation. All right. So if you're running on UV and you don't see any of this, if you don't see any absorption, you can assume that the molecule you're running with doesn't have a benzene ring, carbonyl, or it has no conjugation. Could these two molecules be distinguished using UV spectroscopy? The answer is absolutely not, because both of them contain the same. This will be the chromophore right here. This is the part of the molecule that creates the color. Here is the conjugation, and both are conjugated. All of these will not create. All of this here, all the sp3 CH groups will not produce color, will not produce anything. So therefore, you cannot distinguish these two molecules. But if you have these two molecules here in the bottom, you can definitely distinguish them using UVVs. Yay! Finally, something that it can be useful for. Thank you. And so, yeah, I'm not so excited about this. Sorry. And so, yeah. So here, for this molecule, you can say that the main absorption will be non-bonded to pi star, because that will be your longer lambda, which will be small frequency, low energy, smaller gap. All right. This concludes the second half of chapter 13. Any questions up to this point?
Yeah, quick.
Yes.
On slide 59,
yes,
we
sir.
need to memorize that table pretty much?
No, I will not make you memorize that. No, absolutely not. I don't like my students to memorize stuff. I like my students to analyze stuff. So if I give you a problem that involves UVs, will be most likely telling me your ability to recognize this. Let me show you right here. If it's something that is, so if I give you this molecule, for example, acetone, I'll ask you what kind of absorptions can you predict for this molecule. Then you'll say, okay, definitely will have N to pi star and pi to pi star. If I give you something that has just carbons and double bonds, then you'll say, okay, we can have multiple pi to pi stars. And usually there's 2 of them. That's pretty much it. All right, you see that? So
yeah, thank you.
You're welcome. So this is mostly what I'm interested. Also, notice that if anything is less than 100, you definitely know also. What if I give you, I said to you in words like a molecule has an extinction coefficient of 25, then definitely that should raise for you a flag and say, oh, that must be a non-bonding to pi star absorption because it's smaller than 200. See what I'm saying? Basically, know this little thing here on the top, and you'll be able to solve any other problems. This slide here was just to illustrate you what your eyes see in terms of coloring. All right? So our eyes are limited. But even though with our limitations, we see millions of different hues of color, which is beautiful. It's great. I'm happy with what the Lord gave us because it's enough for me. But when it comes to energy, we can only see through a small window. Otherwise, we'll get our eyes fried with too much power from different gamma rays or UV rays and all that stuff. All right. So that concludes this chapter. I'm going to close it. All right. Yeah, I'm going to save it. Why not? All right. So we'll go back to chapter 13 after we finish chapter 14. So this class runs until, what, 10:40, right? All right. So at 10:40, I'm peeling off to the lab. I'm peeling off my tires. Because there's not much time here in between. All right, so let me lower this down.
I still miss all the tortillas.
Huh?
I still miss all the tortillas.
Yes. You don't want to miss the tortillas. All right. So let's see. Let's go to proton NMR. We're just going to start with proton NMR. All right. So we have we have about 2 weeks worth of NMR that I'm going to teach you. What do I have here? Oh yeah, I have. All right. So here's that. All right. So I'm not going to go through all the details that I talked to you about on my video. Hopefully you've been watching my videos recording from last year. And I explain in good detail how the NMR comes about, how it happens. And so in short words, when you have an energy gap between your molecule and the field that has been applied, because you have a big magnet that is applying energy. If you have a gap, that gap in energy is going to be raised there, and it's going to create a signal. all right, the different functional groups will create that gap in something that is called de-shielding. So the more electron withdrawing groups you have attached to that are closer to the protons that you're studying, that's gonna pull the electrons, because you're polarizing the molecule with the external magnetic field, which is the magnet. And so the more electron withdrawing groups that you have in your molecule, that's going to pull the electrons on your spectrum to the left. So we're going to follow the Beyonce rule, to the left, to the left. Anything you want to the back and to the left, when that happens, that you're dealing with an electron withdrawing group. Whenever you have electron donation, that's going to push your molecule signals what is called upfield. So from 0 to 7 is considered upfield. No. So let's say from 0 to 5 is upfield. From 5 to 14 is downfield. All right. So I also explained what the NMR does, and then we're gonna go back and try to analyze NMRs. All right. Let me pull the complete one so that I can actually talk about it. I'll switch back and forth, and then whenever I have to write, I will write. All right, so let's do that. I'm sorry, it's kind of like a combination right now. I hope you're keeping up with the videos. So I'm here. So I just don't want to write this thing again, because there's not a whole lot to write. But this is a typical spectrum, and this is the spectrum for 3-pentanone. We're gonna be using also. Let me pull that also. That chart that is going to help us out. Important handouts. I'm going to pull this one. So let me pull that, and I'm going to label this. Save as. Browse. In class. All right. So I made this table for you. All right. So I found that from the book, and I round off some of these numbers. Let me see where did I find it, so you can see that I'm not making things up here. But I just saw it on. Every book is different, so every book has like slightly different numbers. But the numbers that I have here are found in page 629. So if I stop the sharing and show it to you, it's this page. All right, it's this page, 679. No, 629. I'm sorry, 629. I took all those numbers and made a better table for you guys. A table that will make more sense, because that's the problem with these books. The people that write these books are very smart, but they don't think like a student. Honestly, they think too abstractly, in my opinion. If you compare that table to the one that I have, mine is better. I'll tell you why it's better. I group everything. And for example, instead of giving you a 0.85, I round it off to a 0.9. That's easier. I use the same numbers, but then they didn't do something that I know that is happening. How to use these base values and apply it to a real life situation. All right. So in the real life situation, what we're going to be doing is, for every, and I want you to fill this out.
Just so you know you're not sharing your screen.
Oh, thank you. Hey, you're my co-pilot today. Thanks a lot, man. All right, let me share back my screen. Thanks to my my man here, Bear. All right. So this is your baseline numbers. So for example, if you have a CH3 group attached to a C, you start off with 0.9. That is what we're gonna call, these are chart values. All these are chart values. All right. Now, let me tell you something, guys. If you master how to use this table, this is how you're going to dissect and identify any molecule in NMR. This is it. This is the holy grail here. All right. So for every group that is CH3, now you have a 0.9. It's fine. But if you have a CH2, you had to add another 0.3 ppms. Means the delta means ppms, which is the number that we're going to be using for NMR. If the group is CH, you have to add 0.7. All right. And if the number is, let me see, hold on a second. If you have a beta group, means 2 away. I explained that here. So if you have a beta group, meaning you say, for example, you have a CH3 and 2 atoms away, you have an atom different than carbon, then you're dealing with something called a beta group. So you're going to have to add 0.3 more. All right. Now, this is the last one. It's kind of interesting. Say, for example, you have a CH2 attached to an OH group and attached in X and attached to a Y group that is, for example, a phenyl. So in other words, you have this OH, CH2, phenyl. All right. You're going to do something. You're going to start, you use the first value on the chart for any of the two. So for example, I would use for the OH, basically I have a carbon, a CH2 to an OH. I will have to use this number. I use 3.3 as my first chart value, because that's a CH3 attached to an oxygen, but I also it's no longer a CH3, it's a CH2, right? So you have to add another 0.3 to that value, and also you have a connection between a carbon. In this case, is a CH2 attached to a phenyl. It'll be this number. So you have 2 chart values that you have to deal with. You can pick either one of the 2 to start off. Basically, what you do is on the second one, you're going to take the second value and subtract 0.9. If you do that, you're going to get very close to the actual where the signal will show up on the NMR. All right. All right. Oh, I think I'm with a couple of stuff. All right. So we're going to be using this to solve most of our NMRs. So,
Dr. Odin,
yes.
I have a question.
Yes.
Why would you subtract there? Why wouldn't you add that to the 2 groups?
You will see that you have to subtract 0.9 because if not, you're going to be off the prediction of where the signal will be.
Okay, thank you.
You're welcome. Yeah, this is just mathematical, but I tell you, it'll work. And we're going to be, remember that we're dealing with a plus or minus 5% of error in science. All right, so we're going to do that. All right. Just to give you an example of NMR. I have done so much NMR in my life. Like when I worked in the pharmaceutical industry, I was an employee for Pfizer for 5 years and then 3 years for Amgen. And I think I must have read about 1,000 NMR spectra per month. So I would read mine, and then I would read like the people that was under me, like the masters. There occasionally a few PhDs that were stuck with their reading their NMR. So I've read a lot of NMR in my entire career. So like if you take, for example, reading 1,000 NMRs per month, 1,000 times 12 months, that's 12,000 a year, plus let's say my 8 years in the industry, plus 3 years at Wake Forest, plus an extra year, let's say in academia, that's 12 times 12. That's 144,000 NMRs easily that I have read in my entire life.
Jeez.
That I think I've read enough. Imagine if I still be in the industry, I'd still be like getting closer to 1 million readings. But I didn't. So 144,000 NMRs in my lifetime, I think that's enough. So I can almost, just by looking at the NMR, I can almost tell, what it is. Funny thing was, like, I never took a formal NMR class. I learned NMR doing research as an undergrad. And then when I went to get my master's, I told my advisor, hey, can I sit on your class? I was just, he was my advisor. He was teaching the class. And I went to the class and I just got bored. The stuff that he was teaching I already knew. I just walked out of the class. I only went like 3 times. So that's bad. Don't skip class. But, I wasn't really raised for that class. But then, now I'm able to teach it. So I'm going to teach you everything I know, all my secrets. I'll pass it on to you. All right. So here's 3-pentanone. 3-pentanone has 2 different signals in the proton NMR. Notice that the carbonyl, we cannot read it in the proton NMR. We'll be able to read it in the carbon NMR. That's different. So notice that when we were doing infrared last week, we were identifying functional groups. That's all the infrared tells. Hey, you have a carbonyl group here, you have a CO group here, and you have an aldehyde group here. But it doesn't tell you how does the structure look like. Now, proton and carbon NMR will tell you and will help you solve the structural backbone of the molecule. It's the most complete, NMR is the most complete elucidation method. In elucidation meaning, you can identify something. Because it stands on its own. But you still need at least two techniques. You can combine proton with carbon NMR. Or you can take proton and infrared, or proton with mass spec. You always will need 2. You need to have a combination. But NMR is the only one that with the same instrument, you can completely identify a molecule by using proton and carbon NMR, because those are the 2 that you will use. All right. So here's a typical proton, and it tells you the chemical shift in ppms. That's the x-axis. It tells you the multiplicity, the number of neighbors in the molecule. So, for example, I see the multiplicity here will be a quartet, because you have 4 peaks for the blue signal, and we have a triplet. We have 3 peaks for the red signal. All right. And also this proton NMR is telling us the integration. The integration tells us how many protons are in each signal. So for this particular case, we have a ratio of 2 to 3. But in reality, that ratio is 4 to 6, right? Mathematically, the Fourier transformation program of the NMR will give you the simplified ratio. In this case, the simplified ratio is 2 to 3. Notice that we also have a TMS standard, which is trimethylsilane, and we use that signal to calibrate the spectrum to 0. All right. Once we calibrate everything to 0, all the other signals will match, and you can reproduce the spectrums of 3 pentanon all the time. All right. So notice that we're going to notice that right now we can just say from this spectrum that, okay, the signal at around 2.2 is a quartet. It integrates for actually 4 hydrogens, and it's a CH2 group. Why is it CH3 group? Because it has a signal of 4. We apply the rule of n plus 1. That's the number of protons plus 1. The number of protons that are neighbors. So this signal in blue for CH2 has 3 neighbors in red. So 3 plus 1 is 4. That will make a quartet. And then the signal in red has a triplet because the CH3 has 2 neighbors next to it in blue, and 2 plus 1 is 3. And 3 is a triplet. And that integrates for 3, but in actuality is 6. So 6 hydrogens. So this is what this proton is telling us. All right. I'm not going to go through this slide much because this just tells you how to calculate the NMR shift in a different NMR depending on its strength, its power. For example, I think we have our 400 megahertz NMR here. That's pretty big. That signal in the 400 megahertz NMR will be the same one on a 300 megahertz NMR, or it will be the same one on a 60 megahertz machine. So, these signals will still be consistent. That's what this light's all about. This light tells you what is downfield, what is upfield. Just simply take the spectrum and cut it in half. From 0 to 5 upfield, from 5 to 10 is downfield. As you do research, you're going to be using more numbers to the left. More complicated molecules will have more complicated NMRs. And so the range usually will be from 0 to 14. This tells you the inductive effect, or that the shielding that happens when you have the different functional groups. And you can see that the signals, they start getting dragged in the spectrum to the left or to the right. And so whenever you have an OH, an NH, or a carboxylic acid, these groups, they vary upon concentration and temperature, and depending on hydrogen bonding. So usually you get a broad singlet with these groups, the OH, the NH, the carboxylic acids. All right. Yeah, this just tells you the different, the pi electron effects whenever you have benzene hydrogens. They're going to be showing around between 7 and 8 when compared to the alkenes that are between 5 and 7. There's always one exception to the rule, and that is the alkynes. So you have a triple bond. So instead of showing downfield, it's the only one that shows upfield for pi systems. And nobody knows how to explain that. It just happens. All right. So that's the exception to the rule. There's always an exception to the rule in chemistry. You can't go around that. And then finally, in this other case, if you have like an aldehyde, it's also, this group is electron withdrawing group, is dragging this H all the way to 10. All right. Remember TMS? The TMS signal was at 0. That's our benchmark signal. And it's 4 CH3 groups here attached to that silo group. All right. So all of them offset each other, and they have the same values, and it is marked at 0. All right. This slide here tells you what a proton equivalence means. So some protons are chemically equivalent. So if you have cyclobutane, all those H's are equivalent. You will have one signal. It will be a singlet, and it will have an integration of 8. On your NMR, the NMR will say, okay, this integrates to 1, right? But it's up to you to know that it's 8 protons if you know the molecular formula of C4 H10. Is it H10? 2, 4, H8. Sorry. Yeah, C4H8. All right. Then you know that it's not 1. That it doesn't have 1 hydrogen. It has to be 8. If your molecular formula was C4H8, we're gonna learn all that. All right. Now remember, we're talking about proton NMRs here. The next molecule has 3 different signals. You have the CH3, and you also have a mirror image. This molecule here will have signals that label A, B, and C. All right. And so notice that the 2 B's are equivalent, the 2 C's are equivalent, the 2 A's are equivalent. So you have to double up the intensity or the integration. So A will be a singlet that it will integrate for 6 hydrogens. The computer will give you number 3. B will be a doublet because it has one neighbor. B has one neighbor in C. Remember, this has hydrogens. So so the B hydrogen has one neighbor, so it integrates for a doublet. 1 plus 1 is 2, and it integrates for 2 hydrogens. The computer will give you a 1 because it's going to give you the lower number for the ratio. So instead of 6 to 2 will be 3, 1, 1. Now notice that C is interesting. C has 2 neighbors. Don't discard this hydrogen here. This is still a neighbor for C. So C will have a neighbor in B, a neighbor in C. And so that will be 2 plus 1 will be a triplet. But the integration wise still goes by the mirror image. And that integrates for 2 hydrogens. All right. Then I talk about geminal hydrogens. Geminal means like twins. Comes from Gemini. And so these are what is called enantiotopic. They will have one signal. They are the same. Now, if you take, they call them enantiotopic because if you take a hydrogen from them and replace it with a different group, then you form a chiral compound. When they are like this, they are enantiotopic. But they have the potential to become chiral, and so that's why they call them enantiotopic, because they can form enantiomers. And if you have the ones on the bottom, in this case, they would be vicinal hydrogens from the Latin vicinus or vecinos. Then you will form, if you plug one hydrogen of those, you will form diastereomers. They will have different signals. In this case, when they are like this, they call them diastereotopics because they have the potential. If you remove one of them, you will turn into a diastereomer. All right. Now, how many of you have watched my analogy with the balconies? Not yet? All right. So where is it? Okay, so this is the way I teach NMR. I compare it to balconies. And in my recording, I go through great detail on that. So we have, for example, this molecule here. We have a CH3, CH2, CH2, OH. Notice that the OH will be a broad singlet. That's an isolated signal, because the oxygen kind of blocks any interaction between this hydrogen and these hydrogens. So that's an isolated signal. It turns into a broad singlet. So I compare this to families living in townhomes, and everybody is, just enjoying the afternoon outside the balcony. We have a family of 3. We have a family of 2 in the next one, and then a family of 2, and then a single rich guy on the right side by itself. So notice that the integration will be 3, 2, 2, and 1. The splitting of the neighbors is what makes the different, what makes NMR fun. So this family here on the left side has 2 neighbors. So they will have an effect on them. So it will be 2 plus 1. They will show us a triplet. So this family right here will be a triplet. The family in the middle, the newlyweds, they will have how many neighbors they have? 5 neighbors. So 5 plus 1 is a sextet. So you need to draw a sextet, meaning 6 peaks. So it will be something like 1, 2, 3, and then they're symmetrical. 4, 5, and 6. This is how this signal will look like for the signal in green. And then the single mother with the daughter on the right side, they have also 2 neighbors, so there will be a triplet. But notice that that triplet will be different than the triplet in red. What is the difference? So this one will be a triplet. The difference is that this will integrate for 2 hydrogens, whereas this other triplet will integrate for 3 hydrogens. That is the difference. They will look the same, but in intensity they will be different. Let me see. I think I have a question here. Yeah. Oh, very good. OA acts as a barrier, causing the signal to be isolated. Very good, Chris, Benjamin. Thank you. That's exactly right. All right. So, yes. So, so these protons here are called exchangeable. Exchangeable. Like that. All right. Very good, Ben. Awesome. Thank you. All right. And so, if you add like deuterium, this OH will be turned into a D, OD. So that's why they're called exchangeable. They're on the deuterated solvents. Sometimes you can make them disappear. And yeah, so the oxygen here is like, it's like Benjamin said, it's like a barrier. Here, these 2 buildings are connected, but they are separated. So all of these are your carbons, and here's your OH signal. And the 2 buildings are connected by a bond. All right. All right. Okay, so at this point, I want to show you how to do this. I'm going to take my time. Oh, I only have 4 minutes. Yeah, let's do at least one. So I'm going to flip here to the clean one and do one. All right. So notice that this molecule right here on the left side is the same as the balcony molecule. All right. And so Yeah, I got 4 minutes. I can finish one in 4 minutes. Let's do one. All right, hold on a second. Let me get my thoughts together. All right, so. All right, here we go. So once you learn how to do this, you'll be lights out good in the lab or in the milestones. All right, I want you to get good at this. So what are we doing here? So first we're going to label the different types of A using letters like A, B, and C. Labeling is important. All right, so we're going to label that. So from left to right away, I'm going to arbitrarily label all this A, B, C, and D. All right. I'm also going to be using this chart. This chart's what's going to help you out tremendously to get those values, and we're gonna see how that works. All right. So the first signal, A. Let's do A. So A in red. So we have A is what? A is a CH3. A CH3 in the chart starts at 0.9. So A is a 0.9. ppms, which is denoted as a delta. It's going to be what? What's the multiplicity of that? We'll learn it. So it has two neighbors, so 2 plus 1 is 3. So it will be a triplet. And it will integrate for 3 hydrogens. All right, B. What is B? All right, so here's where we're going to be using the chart. B is a CH2 attached to a C. So from the chart, it's still this number. That's the closest thing that I have. So B starts at 0.3 plus is a CH3. It's a CH2 group. So where is my, right here. If it's a CH2, I'm going to add 0.3. All right, so I'm going to add 0.3. This takes a little time the first time we do it, but after that, we're going to be faster. So I'm going to add 0.3 because it's a CH2, and I'm also going to add another 0.3 because I have a beta group. Do you see the beta group on the right side? Check this out. I'm looking at this signal right here. So this is alpha, this is beta. I have an oxygen. I have something different than a sp3 carbon. Notice that that's what this says here. Let's see. If there is a group that is two-way, which is different than a normal proton or an sp3 carbon, meaning if you also encounter an sp2 carbon, that will be a beta group. All right? Or if you encounter an sp carbon, that is also considered a beta group. Oh boy, it's 10:40. I'm going to speed up. Just give me 1 sec. And so that's that. So this is total, this 0.9 plus 0.3 plus 0.3, that's 1.5. So 1.5 ppms. It'll be a sextet because it has, signal B has 5 neighbors plus 1, that's 6, and it will integrate to 2 hydrogens. Let's do C real quick. C, it's a, what is the signal for C real quick? Anybody? What will you start here? It's a 3.3, very good. It'll be that one. It's a 3.3. And it's a CH2, so I add 0.3 because it's a CH2. It doesn't have a beta group, so this is equal to 3.6 ppms. It'll be a triplet because it has 2 neighbors, and it will integrate for 2 hydrogen. And finally, D is it's a chart value. It will run from 2 to 5 ppms. It'll be a broad singlet, and it will integrate for 1. All right, I'm going to stop right there, guys. Thank you very much. I will see you on Thursday. We'll continue this. Have a wonderful day. Now you can go ahead and register for Pearson. Thank you.